All right, next up is Teddy Tzanetos, who is the operations lead at JPL for the Ingenuity Mars helicopter program. Teddy, are you there?
Yes, I am. Can you hear me okay?
We can. Thank you.
Fantastic. All right. Thank you all for dialing in, and thank you, James, for such a great intro leading into Ingenuity. Again, great to talk to you all today. My name is Teddy Tzanetos. I'm the Ingenuity team lead, and I'm going to give you guys a brief summary of what we've been able to accomplish over the last 6 months and what's coming up next for Ingenuity on the surface coming out of conjunction. First off, none of this would have been possible without our amazing team. We have a relatively small team that's been working on Ingenuity for almost half a decade now, spanning 3 NASA centers. So, of course, JPL Caltech, Ames Research Center, Langley Research Center, and our industry partners at AeroVironment, Qualcomm, and Solero. I really mean it when I say, none of this would have happened without this fantastic team. So thank you to everyone that's worked on this, and to everyone on the Perseverance team that's worked to help accommodate and integrate Ingenuity and operate it for the last 6 months on the surface. Okay, so first, I wanted to cover some basic terminology. Hopefully, there's a lot of Ingenuity fans in the audience, but it's important to get some definitions straightened out from the beginning. First off, we are a technology demonstrator, which means Ingenuity's core mission from the beginning was to prove that we can fly on Mars. It does not carry a science payload. It does not have a core science mission from its tech demo objectives. If you allow the Star Trek reference, our prime directive was to prove that we can fly on Mars. That's it. And I don't mean it lightly when I say we wanted to have our Wright brothers moment. We mean that in every sense of the word. Just like 120 years ago, humanity proved that we can fly here on Earth. The goal was to prove that we can fly on Mars, to provide that foundation to the future, and really see that explosion of aerial exploration on Mars in the decades to come. For each one of our flights, we're bringing back a treasure trove of information, a treasure trove of engineering data that future generations are going to rely on when they look back and say, what did Ingenuity do, and what do we want to do in the future if we want to carry actual science payloads or do different types of exploration? How can we build on that? On board, we have a 13 megapixel color imager, a 0.5 megapixel black and white imager. Of course, we have an IMU to help us fly around on the surface, laser altimeter. And we're also looking at environmental data. So what is the solar panel situation? How much energy are we generating? What is the solar insolation hitting our solar panel? We have temperature sensors throughout the aircraft. And the most unique data set is actually the flight dynamics, right? Compared to everything else we've sent out into space, this is going to be the first time where we have a flight dynamics data set of an aircraft, a powered, heavier than air aircraft that's behaving autonomously on the surface, and comparing and asking the questions, well, what do our models say the aircraft should be doing, and how is the aircraft actually performing? And that delta, that's the knowledge gained, right? That's the advantage of having your asset on the surface and actually in operation. And just like Sojourner gave rise to the extremely capable Perseverance rover that we have today, and it started its humble origins as a tech demo, size of a microwave, and now we have large car-sized rovers on Mars. We share the dream that we want to see fleets of aircraft on Mars one day, either carrying out science missions or helping future potential human explorers, like James was showing a couple of minutes ago. So can't wait to see that one day. And I'm extremely happy and proud to say that the tech demo is complete. We could end the slideshow here and say we've done it, but it is true. The original technology demonstration mission was a 30-sol operation, and in those 30 sols, the objective was to A, prove that we can fly, and B, try and execute 4 additional flights within those 30 sols. We succeeded in that dream, in that vision, and by the end of it, thankfully, because the vehicle was still healthy and because there was still value to be provided and lessons to be learned, NASA decided to continue the Ingenuity mission and transition it from a tech demo, where, like I said, the prime directive was prove we can fly. That's it, to an operations demo, which is what we're currently in. And the goal of our operations demo is to keep pushing the envelope. What else can we learn about flying a helicopter on Mars? From a human to aircraft interaction standpoint, how to improve operations, But also, what can we do better on the aircraft front? Can we expand our distance horizon? Can we fly for longer? Can we increase the capabilities of the aircraft and make it a more valuable tool for the Perseverance team to levy? And that's been our mode of operation since May 8th. And over the last 6 months, we've been trying to keep pushing that edge and keep improving the quality of scouting capabilities that we're able to return for the Perseverance team. So this all started, with launch back in July of 2020. We arrived and we hitched a ride under the belly of Perseverance. I went through EDL in February. And on this bottom right image, you can see this actually visualization. And this visualization, you can see this black container. And James was actually showing an image of our debris shield. We were the lowest point coming down from EDL. And that debris shield was there to protect us from any dust, rocks, pebbles that would be flying around as we went through the sky crane maneuver. During cruise, we were relatively quiet and relatively low level in terms of the activities going on with the helicopter. We have 6 lithium-ion batteries on board, and just like with your cell phone, if you leave it on your table for a while, the battery will start to discharge. So once every 2 weeks, we would do a charge activity in the 6.5-month cruise from Earth to Mars. Here's an image from Atlo that gives you a better idea of how we were packaged and stowed in the belly of the rover. We had to be rotated sideways, and our legs needed to be folded up across the rotor system. You can see our solar panel here and our coaxial rotor system. So the 2 rotors spin opposite from each other, and that's how you produce lift. We can get into controls if you guys have some questions later. This is the same image James was showing of our debris shield being dropped. And the rover actually drove over the debris shield when we were ready for deployment, and brought us to our first home on Mars, what we call Wright Brothers Field. That was an area on Mars specifically chosen for its rock density and slopes and safety for our first flights on Mars. We wanted to make sure we could pick the clearest parking lot, so to speak, in the immediate vicinity of Perseverance to be deployed onto. This is a GIF showing the full sequence animation of the complicated deployment sequence. I do want to take a moment here and congratulate the Perseverance operations team for all of the intricate work that had to go into making sure that each one of these firings and deployments worked, and the autonomy, especially towards the end of it, worked as planned. It's important to realize that once we were deployed from Perseverance, there's no going back. We can't reattach the umbilical. We can't go back to the rover for recharging. So we need to be self-sufficient immediately as soon as all 4 feet touch the ground. And that also, the biggest challenge there is being self-sufficient in terms of just thermal survival, right? So as soon as our feet touch the ground, we start draining our battery to warm ourselves constantly throughout a sol. And there was a lot of challenges that went into making sure that the rover was able to drive off of the helicopter as quickly as possible and as safely as possible. Once all parties involved were confident that the helicopter had safely deployed. And there's some interesting papers coming out soon that'll detail a little more about this fascinating process and the challenges involved. So please encourage everyone to check those out in a couple of months. But we were finally on the surface. We were finally deployed, healthy and stable, and ready to begin our core mission of proving that we could fly. Just like with aircraft here on Earth, there's a lot of pre-flight checks that we had to go through to make sure that the rotor system was healthy and made it through the journey from Earth over to Mars. We had to go through a blade release sequence, which you see here on the left side. We had some mechanisms that were responsible for making sure that the blades didn't move at all throughout the entire journey. So effectively, flexing your wings a little bit and making sure that everything's free and ready to move. We then did a 50 RPM spin test, again, just progressing further along the spectrum of being ready for a flight. And we got all green across the board. And you might be wondering, okay, we're going through all of these difficulties, all of these challenges. Why? So what? What's the difficulty with flying on Mars? We're good at flying here on Earth. The simple answer is the air density, right? It's 1% the density of Earth's. And most of the design and engineering challenges boil down or derive from that. Yes, the gravity is 1/3 that of Earth's, but it's still a bad trade overall if you had to pick which planet you'd rather fly on. From that 1% density, and several engineering directives, or you could think of commandments, flow down from that. Given a fixed volume under the rover that we were able to be carved out for us, those directives are the following. You want to make sure your blades are as large as possible to catch as much air, as much of that 1% density air as you can. You want to spin those blades very, very fast, again, to produce enough thrust to fly. And you also want to be very, very light, okay? And that in and of itself, staying underneath the 1.8 kilograms, it deserves its own talk and its own paper on the engineering challenges of producing an autonomous, fully self-sufficient aircraft and be that light. Two other things I'll point out in this image we can talk about later. You'll see our solar panel up top. So we have 3 strings of 10 stacks of solar cells, and you also see our antenna. This whip antenna is our 900 megahertz link back to humanity. That's how the helicopter talks to the rover. We have a base station on the rover, and you can think of that as our man in the middle. So all the data that the rover needs to send to the helicopter goes to the base station, forwarded over to Ingenuity, and likewise, all of the data, the flight data, engineering data, color imagery, and black and white imagery, that all gets sent back from the helicopter to the base station and back to everyone on the control room. And it all led to this very first flight. In comparison to what we've been able to accomplish recently, it seems like a pretty simple and humble beginning of our flight log, but this really was the moment that the entire team had been waiting for years, to prove for NASA and to prove for humanity that yes, we can do this. We're not limited to just Earth. We can fly on Mars. And it was a simple 3-meter pop-up hover for 39 seconds and come back down and land. But this really is the shining moment of the entire Ingenuity mission. And everything that followed has built on that, right? And we've been trying to get better at flying for further distances, for increased amount of time, for getting better imagery back, not just for ourselves for technology demonstration purposes, but more and more, especially over the last 5 flights, and James showed a couple of scouting images that we've been able to take. We want to improve the value of Ingenuity as a tool, as a scouting resource for the Perseverance science team and the rover planning team. Here's one of the happiest moments in my life, and I'm sure in most everyone's life here in this image, was our first flight in our control room. Just like with pilots here on Earth, you need to trust your instruments and your gauges. You might not always be able to look outside the window and see where you're flying or how you're doing on your flight path. And that's no different than with aircraft on Mars. The way the deep space network works and the way negotiating data transmissions work is you don't get all your data immediately. Sometimes you'll get a trickle of data and you'll just get a little bit at a time. And it was critical that we all decided what would be our metric, what would be our success criteria for that first flight, and what would be the smallest amount of data that was still sufficient to confirm that we flew and we landed successfully. And that was our altimeter. So you see us all freaking out, staring at us. What looks like a simple plot to most of you was a very meaningful plot, which our chief pilot decided was the altimeter. And seeing the altimeter report that we had gone 3 meters up, held, and then came back down after 39 seconds was sufficient to confirm that, yes, we've done it, we've flown on Mars, and we're safe on the surface. Here's a zoom-in view of that altimeter, which I have framed, and I will keep in a special place in my home for the rest of my life, and I'm sure the rest of the team feels the same way. This plot matched perfectly with what our simulations expectations were, and that's why we're able to confirm, yes, Ingenuity flew, and not only did we fly, we came back down and landed, and we survived landing. Shortly after the first altimeter readings, we started seeing some images from that flight. Here is one of the coolest mid-flight images of our shadow. So we have a nadir-pointed black and white imager, and you can see the blades and the feet here very, very clearly, and this rectangle is actually our solar panel, as we did our simple 3-meter hover for our first flight. You can also see the rover tracks that Perseverance left for us as nice framing features as it drove over the helicopter to its safe observing location. Since then, since that important critical Wright brothers flight on Mars, we've stayed busy. This is our total life in one image since our first flight and since deployment, since up to Sol 214. There are two paths you see in this map. There's the white path, which is that's the path that Perseverance has taken all along with us, and then the green path is all of our flight paths stitched together that we've followed along Perseverance with. We started off in this blue box here where we had flights 1 through 3. Flights 4 through 5 extended us further down, and then we really started spreading our wings, so to speak, and started going for distance and pushing the limits more and more of what Ingenuity was capable of. So you can see flight 6, 7, 8, and our most daring flight to date was flight 9, where we covered 625 meters. And then we really started focusing more on what sort of flights could we do that the scientists were extremely interested in. So with flight 10, we went to the Rays Ridges area. And here's where we really got better at understanding and speaking with the scientists on Perseverance to understand what is considered a win here in terms of scouting. And it's not just find the coolest outcrop. It could also be confirm that this outcrop is not interesting, right? That's still a win for both teams here to say, if there's no longer a need to dedicate souls and resources towards exploring that hill, great. The Perseverance team can then focus on going to a different location. I want to remind everyone, the whole goal here of Perseverance is to collect samples and prepare those samples to come back home. So if there's in any way that Ingenuity can help make that process more efficient through these scouting flights, that's what we're after here in our ops demo. That's what we're looking for. How can we help in any way possible improve that efficiency? And while we're at it, continue to learn lessons about what it's like to fly on Mars. Flights 11, 12, and the most exciting one, I think from a science perspective, or maybe just because it's the most recent success to date, is Flight 13. And I'll talk a little bit more about Flight 13 before we talk about what comes next. In summary, we've covered almost 2.9 kilometers total on the surface. It's a big leap forward from our first flight, which covered 0 meters horizontally. It was just 3 meters vertically. And total time flown now is about 24 minutes and 29 seconds. Again, a large explosion from our first 39.1 second flight that we've had. Here is a graphical representation of our life to date. So you can pick your favorite aircraft metric, whether or not it's distance, flight time, velocity, or accumulated distance, and I'll let you pick which y-axis you want to look at. But instead of spending too much time on each individual segment, I just wanted to comment on the trends here. On flights 1 through 5, you can see that we really tried on all of these functions here, progress as much as we could, right? How far can we fly? Let's fly further. Let's fly for a longer period of time. Let's fly faster. And then you can see as we moved into the operations demonstration, right? We still wanted to push those limits, but the focus has started changing, right? It's not the case that in flight 10 or specifically in flight 13 that the vehicle was performing differently than in the past, but actually we wanted to slow down. So for example, in flight 13 here, you see that velocity, we started flying slower. We wanted to fly slower so that we can capture better imagery. We covered less distance because we wanted to loiter over a single outcrop. And we're going to continue doing that. And we're excited to have these targeted flights in the future because that's where we think we can offer the most value to the Perseverance team. But also, we're still learning more. It's not just about fly as far as you can. There are aspects to operations that we're trying to, write the book on. No one's ever done this before, and we're learning lessons about how to capture better scouting images, how to capture better stereo products and three-dimensional images. And we're excited to keep doing that mission. So I'll talk about our most recent flight and then what comes up next, and then I think I'll save some time if there's any questions. So on the left-hand side is our orbital view again, just to orient everyone, where we started, how far we've come. And in this blue circle, we're zooming in on a specific outcrop called Faiafu. And I apologize if I'm butchering the French pronunciation there. Our flight 13, you can see, took this U path where we wanted to fly around this outcrop and take a series of color images pointing towards the southwest to get as much resolution as we could on that specific outcrop, and fly slowly for that reason. This GIF, animated GIF blink, gives you a sense for the improvement in resolution and the improvement in scale. What does an aircraft actually provide, right? Because it's a reasonable question. We have satellites orbiting Mars, and we have rovers, and we have landers. Why fly an aircraft over an area? What does it provide in terms of resolution, and what does it provide in terms of scouting capability? So at this higher altitude, you can see the increase in resolution. And when we zoom in here, you get a much better sense for what aircraft are capable of providing to mission planners versus what orbiters are capable of providing. And it's not just in the context of these orbital images. Because we know how far away we were from each one of our color images, you can use that data and stitch together a three-dimensional map and actually get stereo matches across your entire imaging set. And that's what several people have worked on. Here's an example of what that three-dimensional view of this Faiafu outcrop looks like. And this is, in my book, one of the coolest data products that have come out of our flights. Being able to zoom in and walk through these three-dimensional environment, right, just based off of helicopter imagery, I hope is going to inspire generations to come for aerial exploration and flights to come. You know, we still want to keep providing this valuable resource to the Perseverance team for as long as we can, and we still want to keep learning lessons about flying aircraft on Mars. Okay, so finally, what's next? So after Flight 13, we started preparing for the future months ahead of us in terms of seasonal low density. So I'll remind everyone that our original technology demonstrator mission was 30 sols, and we've been flying for 6 months now. While that's been happening, Mars has been moving around the sun, and we're moving into an area of the season where the density is dropping. The way you account for that with a rotorcraft is as density drops, you need to spin your blades faster. So we're used to spinning. Our target set point for our flights thus far has been 2537 RPM. And we need to bump that up to closer to 2800 RPM to account for the seasonal drop in density. So right before conjunction, we did a low density rotor checkout, which looks similar to what we did in commissioning, where we stay on the ground and we just spin the blades up to a high RPM, confirm that the system is behaving as expected. There's no mechanical resonances or vibrations, and that was a great success. We then tried doing Flight 14. And for those of you following along on the blog, on the Mars 2020 website, there's a Ingenuity blog. I encourage you all to check it out. And there have been very detailed write-ups of what's gone right, what's gone wrong, post-flight analysis, pre-flight briefings. You can find a lot of great detail month to month about what our plans are there. And there's a great write-up about our Flight 14 first attempt. And what happened is we did a pre-flight check. In each of our flights, we do a pre-flight check where we flare the blades and we go through just a checkout to make sure that everything's looking good. Unfortunately, the pre-flight checks did not return a thumbs up, and the vehicle did what it was supposed to do, which is just scrub the flight. We've since then looked at the data, performed additional checks. Things are looking good for the vehicle. And then we went into conjunction. So we've been sitting down on the surface in the same location we were after Flight 13. And starting next week, we'll pick up operations again, and we're looking forward to doing a post-conjunction comms check, make sure that the vehicle's healthy and responding, and we'll check out our rotor system again, and then we'll move on to reattempting Flight 14, confirm that the vehicle is working in this lower density seasonal environment now, where we're spinning blades faster, and then pick up where we left off. We're excited to continue the scouting mission with Flight 15 moving forward, and can't wait to see what comes next. That's all I have for today. Thank you very much for your time, and happy to answer any questions if there's any time left.
Thanks, Teddy. Handing this over to Sagar for your Q&A.
Hi, Teddy. I hope you can hear me.
Yes.
So I have a few questions for you from the audience side. And the first question is, how much dust is accumulating on the solar panels, and does the flying help with clean that off?
Sure. So we have not found a trend in our solar panel data to indicate that there's been accumulation of dust on the solar panel. That's not to say that we're certain that there's a self-cleaning effect from flights. That's an aspect of ongoing analysis that we're doing from flight to flight. Coming out of conjunction, actually, this will be a good data point for that since we've been standing still for several weeks. But that's still ongoing question. I'm happy to say, though, that across our 13 flights, we have not seen any trend in decrease in solar array performance and total number of watt hours we're able to ingest in the battery. The battery in the solar system, the battery in the solar panel, rather, are behaving just as well as they were on Sol 43 when we were deployed.
Okay, so the next question is, what will be the limiting factor for how long Ingenuity can operate? As we have already mentioned that it has already passed its time there.
Yeah, so that's a great point to start on. We've already passed the design limit, which was 30 sols. And there are several aspects to that question. There's just the mechanical and assembly aspect to it, where because everything was rated for 30 sols, there may be a point at which certain components start aging. And that's something we're tracking from flight to flight. And then there's also the environmental aspect of that question, which is what does Mars have in store for us in terms of solar insolation, in terms of thermals, and the continuing variation of density that comes along with that. We're looking ahead several months out, and thermally things will start getting warmer for us, which is nicer where we are. The thermal insulation will start to drop. So we'll start getting less energy. But overall, those are manageable challenges, right? We can design flights around that. So it'll be a combination of just time, right? Just like I said, we were only designed for 30 sols, and keeping track of each one of our components, from our electronics to our actuators to our servo mechanisms and rotor motors. Happy to say, though, that there's no immediate sign of aging, but we are keeping track of that.
Sagar, do you have another question?
Yeah, so we have one more question from Holger. So how are those nice color images that you have taken, like the most high in that, and the camera view angle? So basically he's asking whether the helicopter is able to tilt and take photos in different angles, or whether those are stationary.
Sure. So the camera is stationary within the frame of the helicopter. So it is possible to try and design flights and time the images when we're changing orientation, right? So if we're flying forward and then stop, the way you stop on helicopters, you lean counter to your momentum, right? And timing an image right when that occurs, that is possible. And we've discussed, the challenges about trying to design that. It's a timing question, right? How well can you time the exact moment where you take the image versus where the vehicle is in its trajectory? So there's examples of when we tried doing that in prior flights, actually, to get those images while we were leaning. But it's a challenge. It's definitely a challenge to attempt that. So doing stationary scouting or horizontal scouting is definitely the primary means of imaging that we've been doing.
Looks like we have a question from AltSpace VR. AltSpace, go ahead.
Yeah, thanks so much. I understand you're using a processor that's basically from a commercial cell phone of sorts, and
Yes.
very simple. And I'm curious, just how easy is this to maybe replicate and attach to future rovers? It seems like you could drop one of these from the bottom. Also, kind of curious, can we scale it down? We talked a little bit last with Jim about scaling up, but can it be scaled down to be smaller? And is there any reason to do that?
Sure. So if I think I understood the first question, can we have one of these processors on the rover? We actually do. So the same exact Snapdragon processor that we have. So it's a Qualcomm 801 Snapdragon on the helicopter. We have the exact replica, almost replica of the rest of the avionics, but that same processor is on the helicopter base station, which is attached to the rover. So that is already there. And in terms of future rovers, right, being able to fly these commercial off-the-shelf, very powerful processors is definitely an exciting opportunity in terms of compute power on Mars, right? There's always this challenge between producing data and sending the data back to Earth so we can crunch the data here on the ground with data centers versus can you have that compute resource available to you on the surface and try and digest that data. So it's definitely an exciting opportunity. And then on your second question in terms of scaling down. So scaling down, it just becomes harder and harder to fit within your mass margins, or rather to fit a vehicle that's can carry enough energy and can still fly a meaningful flight, right? You need to ask yourself, we can go smaller, your batteries are going to shrink, everything's going to shrink. What is the useful mission of a smaller rotorcraft compared to a larger one? So you can scale down, but everything will scale down with you. And for Ingenuity, right, it was the opposite question. We had a not to exceed volume, and we wanted to fill that as much as we could to make the most capable technology demonstrator possible.
Thanks, Teddy. We're out of time. I just have to tell you, those Ingenuity flights make all of our hearts leap. So congratulations
Thank you very much.
on that Wright Brothers moment. And thanks for being with us.
Appreciate it.